This problem is in the context of web work problem 4 from homework 4. Hope I should let everybody in. And so this question is asking about a function like this. F of x equal to, I'm going to pick cosine instead of sine. Let's say that cosine of 5x over 3 plus x. So here's the thing to know about sine and cosine. Sine, how's the lighting? Let me know if the lighting is, that seems, I don't know, it's always a challenge. Let me know if the lighting is terrible, but I think it's all right. So, yeah, and we'll definitely talk about limit Trig function for sure. Sorry, was someone saying something? So sine and cosine on their own. So g of x equal to sine of x, h of x equal to cosine of x. These functions are continuous everywhere. In fact, there's a lot of functions that are continuous everywhere. So is e to the x, so is 2 to the x. Any exponential function like that, also continuous. I should write like, f of x equals e to the x, or g of x equals 2 to the x. Any polynomial, right? F of x equals x to the third plus 5x squared minus 2x plus 1.
Is there any way that you could move like the board a little bit closer or something? Because it's blurry for everyone. Please.
Oh, let me see. I feel like there was a reason it was blurry before. Let me make sure I don't have anything stupid open. 1 second. Oh, come on. Sorry, sometimes I've been uploading videos before. How's that? Is that a little better? No, it's still blurry. What could be going on? Let me see. No. Oh, why is iTunes open? That's stupid. I didn't have you. I'm trying to close everything, make sure there's nothing idiotic. Things look more easy to see now.
It looks better.
Oh, good. All right. Yeah, sorry. Sometimes I don't know why iTunes is open. It's not like I'm using it. All right. You're very welcome. Yeah. Please let me know in general. I got to make sure things are closed. All right. So lots of functions we deal with are continuous everywhere. Sine, cosine, e to the x, 2 to the x, any polynomial. Those are kind of the main ones. Other trig functions like tangent and cotangent and secant and cosecant, they're continuous where they're defined. Right? The tangent, cotangent, secant, cosecant are undefined places. The same is true for rational functions. Right? A function like g of x equal to 6x squared plus 2 over x squared minus 1. This function is continuous everywhere that it's defined. It's not defined at plus or minus 1, right? Because if you plug in plus or minus 1, you get division by 0. But everywhere else, this is continuous on its domain, which would be everything from negative infinity to negative 1, and then negative 1 to 1, and then 1 to infinity. So this function here, cosine of 5x over 3 plus x, is continuous as long as it's defined. So where is this function undefined? Well, it's undefined when the denominator of the inside there is 0. So it's undefined when x plus 3 equals 0, or when x equals negative 3. And that's the only place where it's undefined. So if we look at this one, it's going to be continuous everywhere else. And that is true for a lot of functions, is that as long as they're defined, they're continuous. There are some exceptions to that, but most of the time, that's really what we're looking for. Is you're looking for, well, is this function undefined somewhere? Then it's discontinuous there. As long as it's defined everywhere else, most of the time that means it's continuous. There are definitely some examples where that's not true, but most of the examples that you'll see of discontinuous functions, where a function is defined but still discontinuous, are piecewise functions. So like, let me give you another example. Let me grab another example here. Not you. Sure. So for example, this function, f of x equal to 2x over x squared minus 3x minus 4. It's a rational function. It's defined, or it's continuous on its domain. And if we factor the denominator, which factors is x minus 4 times x plus 1, we can see that it's undefined at x equal to 4 and x equal to negative 1. So it's continuous everywhere else. So it's continuous on the interval from negative infinity to negative 1, union negative 1 to 4, union 4 to infinity. Sometimes we define piecewise functions that are still defined at a point, but also discontinuous there. For example, the function f of x equal to, let's say, I don't know, 3x plus 2 when x is less than or equal to 1, and 5x plus 1 when x is greater than 1. This piecewise function is defined everywhere, right? F of 1 exists, f of anything exists. But this function is definitely discontinuous at x equal to 1. Not because it's not defined there, although that's certainly one way a function can be discontinuous, but because the limit doesn't exist at 1. Right? If we take the limit as x approaches 1 from the left of this function, that's going to be the limit as x approaches 1 from the left of this piece where x is less than 1, which is 3x plus 2. And then we can just plug in 1 and get 3 plus 2, which is 5. On the other side, the limit as x approaches 1 from the right of this function is going to be the limit as x approaches 1 from the right of 5x plus 1. And if we plug in 1 there, we get 6. And since the right-hand limit and left-hand limit aren't matching up, the function is not continuous there. So this function is an example of where it's still defined everywhere, especially at 1, but it's not continuous at 1. Whereas this function, it's only not continuous where it's not defined. So most normal functions, regular functions, functions that aren't piecewise functions, most regular functions are continuous where they're defined, or as we say, they are continuous on their domains. But piecewise functions often are used as examples of functions that are discontinuous at places where they're still defined. Yeah, let me see here. Yeah. Oh yeah, sorry. Sure. So let's see. Let's look at this. So then, yeah, I want to feel like we'll just go all over the place. We'll just go in order. So I'm going to look at this question that someone asked, and then we'll get back to the other one. Where'd you go? Sure. So let's look at this question. We did one kind of like this last time, but I think it's worth seeing this again. I want to look at the limit as x goes to infinity and the limit as x goes to minus infinity of the following expression. I'm going to change this up just slightly from the one Vinny asked. So I'm going to say I'm going to make it actually not terrible this time. So 3e to the 7x over, on the bottom, yeah, 8e to the 7x plus 6e to the 8x. And I want to find the limit as x goes to infinity and negative infinity. And so for either one of these problems, and again, when we look at limits like this in general, the thing you want to think about is dividing the top and the bottom by the thing that's getting the biggest, the fastest. Or you could also say the smallest, the slowest. Right, that's another way you could think of it. So in this example, when x is going to infinity, e to the 8x is the thing that's growing the fastest. So I'm going to divide everything by e to the 8x. And I'm going to, so e to the 7x divided by e to the 8x, right? I'm going to get e to the 7x over e to the 8x. On the bottom, I'm going to get 8 e to the 7x over e to the 8x. And then I'm going to get 6 e to the 8x over e to the 8x. This is going to be the limit as x goes to infinity of, so e to the 7x over e to the 8x is either e to the negative x or 1 over e to the x. I prefer 1 over e to the x or 3 over e to the x. And the denominator, 8 e to the 7x over e to the 8x is 8 over e to the x. And here I get 6. And now as x goes to infinity, 3 over e to the x goes to 0. 8 over e to the x goes to 0. 6 is 6. So this is 0 over 0 plus 6, which is 0. Sorry, my 6 can look like 0 sometimes. On the other side, we don't want to divide by e to the 8x anymore. We want to divide by e to the 7x. So I should point out, as we're going to negative infinity, all of these things are going to 0. That's going to 0, that's going to 0, that's going to 0. So it's not that we're dividing by the thing that's getting biggest, we're dividing by the thing that's getting smallest, the slowest, if that makes sense. E to the 8x is getting smallest, the fastest. So the things that get biggest, the fastest also get smallest, the fastest. So I'm going to divide everything by e to the 7x. So here I'm going to get the limit as x goes to minus infinity. So 3 e to the 7x over e to the 7x is 3. 8 e to the 7x over e to the 7x is 8. And 6 e to the 8x over e to the 7x is 6 e to the x. And now as x goes to minus infinity, 6 e to the x goes to 0. And so you're left with 3/8. So the idea is if you divide by the right thing, the leftover parts are going to go to 0. And so you can figure out what this is actually approaching. Questions about either one of these?
So when we're doing the limit as x is approaching positive infinity,
yes,
we do the greatest one on the bottom, right?
Yeah, you're right. That's a good clarification, Melody. In this case, the greatest one is the greatest one on the bottom, but you're right. In the example I did last class, I made the mistake of dividing by the greatest one overall, and that got me kind of stuck. So you're definitely right. You want to divide by the thing that's getting biggest, the fastest, that's in the denominator. Excellent point.
Oh, so that also applies to negative infinity?
Yes. Well, so again, so for negative infinity, though, you want to be careful. Right? It's the thing that's getting biggest or that's not getting smallest, but the roles change, right? For negative infinity, the thing that's getting big, the thing that's the bigger thing is the e to the 7x.
Yeah. Oh, but I mean like you choose the one that gets, okay, the thing that you're saying, but on the denominator, right?
Yes, always in the denominator. You're totally right. Yeah.
What if there's only like one with the ex on the bottom though? Because then each time you would have to divide over the same thing?
Yes, that's true.
Okay.
And so that'll probably end up then in that example, you'll probably end up with one of the limits being infinite, most likely. Okay,
Wait, I had a question on the when the limit is x approaching to negative infinity.
Yep.
And then instead of going to the 8x, why did you do the 7x?
So here's the reason why. Let me actually show you guys. Let me make it easier. So I would try graphing it, but I'm just going to graph on Desmos instead. So let me show you why. Let me show my screen. Share some Desmos. Yeah. Okay. So the reason why is because if you graph y equals, well, come on, if you try to graph y equals e to the 8x. I keep wanting to use braces. Sorry, I'm used to using braces when I type in a different program. And then if we do y equals e to the 7x. Now it's hard to see because they're very close to each other. If we zoom in a bit, you will notice that the red one is bigger to the right. I mean, it's hard to write. They're very close to each other, but the red one's definitely bigger as you go to the right. So e to the 8x is the larger one as you go to infinity. But as you go to negative infinity, the blue one is the larger one. E to the 7x is the larger one. So that's what I'm trying to keep in line with the idea that I'm always dividing by the thing that's the larger thing. And as I'm going to negative infinity, the larger thing is e to the 7x, not e to the 8x.
Okay. Thank you.
Yeah, you're welcome. Okay, so the reason I wanted to do that problem before is because someone asked me about problem 32 in chapter 2.4, and I think this is kind of a good lead up to that problem. So, but you can only listen to another problem. All right, so let me see here. Where did you go? So this problem's a little bit wordy. So let me read it. It's again problem 32 in section 2.4 of your textbook. So it says genes produce molecules called mRNA that go on to produce proteins. High concentrations of protein inhibit the production of mRNA, leading to stable gene regulation. This process has been modeled, and they talk about it more in section 10.3, to show the concentration of mRNA over time is given by the equation m of t. So that's the concentration of mRNA is equal to 1/2 e to the negative t times sine of t minus cosine of t plus 1/2. And they ask us two questions. The first is to ask us to evaluate the limit as t goes to 0 of this expression. And then the second question is to evaluate the limit as t goes to infinity of this expression. Okay. So let's look at the first part. The first part shouldn't be, oh, and it also talks about interpreting results, which, you know, we'll see if we can do. So here, I'm just going to do the limit as t goes to 0 of 1/2 e to the negative t times sine of t minus cosine of t plus 1/2. And again, when we're taking a limit, sorry, I'm not keeping up with the chat because there's lots of things up here. Yeah, sorry, it's 2.0. Yeah. The first thing I do when I take a limit is I just try and plug in what t is approaching, whatever what x is approaching, right? So I'm just going to try plugging in 0 for t. We get 1/2 e to the 0 times sine of 0 minus cosine of 0 plus 1/2. So that says I've got, let's see, so e to the 0 is 1. So 1/2 times 1 times sine of 0 is 0, cosine of 0 is 1 plus 1/2. So I get 1/2 times -1, so -1/2 plus 1/2, which is 0. And then it asks us to interpret the results. So again, this thing we are modeling is the concentration of mRNA over time. So this is saying as time approaches 0, the concentration gets closer and closer to 0. That seems, I mean, I guess if you're starting out, I don't know. I don't know if that really makes a lot of sense. I might look at section 10.3 to get a better idea of what this means. Well, let's talk about the other part, because that's the part the part I really want to talk about was limit to infinity. So I'm just going to erase this up here and write the limit to infinity. Now, there's a problem. And the problem is you have a limit to infinity with a sine or a cosine. In fact, we have sine and cosine. And most of the time, when you have a limit to infinity involving a sine or a cosine, you usually have to use the squeeze theorem. And so it's especially tricky when you have sine and cosine. So here's what I'm going to do. I'm going to say, I know for sure that sine of t minus cosine of t, I don't know how big that ever actually gets, but I know it's always less than or equal to 2. I know it's less than or equal to 2 because sine is always less than or equal to 1 and cosine is always less than or equal to 1. And bigger than or equal to -1 and bigger than, right? So since both of these are between 1 and -1, if you add or subtract them, you're definitely going to be less than or equal to 2. And in a similar way, bigger than or equal to -2. You're probably actually never going to get to 2, right? If you graph sine minus cosine, it might look like it gets close to 2 sometimes. It probably never actually is 2. It might be, I don't know for sure. But we know this for sure. And so then what we can do, and this is always the case, most of the time the case, you start with some compound inequality that you know is true. And then you try and manipulate the middle part so it looks like the thing you're actually trying to take the limit of. So I'm going to take this sine t minus cosine t, and first I'm going to multiply it by 1/2 e to the -t. But I can't just do it to the middle. I have to do it to each of the 3 parts. So I multiply everything by 1/2 e to the -t. So -2 times 1/2 e to the -t is less than or equal to 1/2 e to the -t times sine of t minus cosine of t is less than or equal to 1/2 e to the -t times 2. Okay, so then we can do a couple things. One, you can cancel some 2's. And 2, we also need to add on this 1/2 to everything. So I'm going to rewrite this as -e to the -t plus 1/2 is less than or equal to 1/2 e to the -t times sine of t minus cosine of t plus 1/2 is less than or equal to e to the -t plus 1/2. Okay, let me admit the person here. Lots of folks today. Okay, so now here's what we've got. We've got the thing that we're trying to take the limit of, 1/2 e to the -t times sine t minus cosine t plus 1/2. We've got that stuck between 2 things. And what we're going to do now is we're going to take the limit of those things and see what we get. And the goal for the squeeze theorem to work is that the limit of this and the limit of this are the same, so that the limit of this is smushed between them. Well, let's find out. So the limit as t goes to infinity of -e to the -t plus 1/2. Well, as t goes to infinity, e to the -t goes to 0. So I end up with 0 plus 1/2, which is 1/2. Okay, let's do the same thing over here. The limit as t goes to infinity of e to the -t plus 1/2. Well, same thing's going to happen. E to the -t goes to 0, and 0 plus 1/2 is going to be 1/2. And now here's what we get to say. Since the limit of this is 1/2, and the limit of this is 1/2, by the squeeze theorem, the limit of the thing between them has to be between them. So you have to be between 1/2 and 1/2, which means you have to be 1/2. So we can say this is equal to 1/2 by the squeeze theorem. And this is generally how the squeeze theorem works. You get the thing you're trying to take the limit of between two other things, and the limits of those two other things are equal to the same thing. They have to be the same thing for the squeeze theorem to work. And as far as interpreting that, I would say that means that the concentration of mRNA over time gets closer and closer to 1/2 as time goes on and on and on and on and on. Are there other things we should say about this? So that's a good question, Michaela. No, so let me actually, that actually brings up more of what we want to do. So let me talk about another one. So a kind of more classic example is maybe saying, what's the limit as x goes to infinity of sine of x over x? And so here's my thought process almost always. When I have a limit to infinity and a sine or a cosine, I don't know what's happening, right? Because I know that sine, right, y equals sine of x, does this kind of thing, right? And as x goes to infinity, it just keeps bouncing back and forth and back and forth and back and forth between 1 and -1, right? Not getting close to any one particular value. So what I think about is, oh, when x is going to infinity, I don't know what sine of x is doing, but I do know that it's stuck or bounded between the values of 1 and -1. So to answer the general question there, I would say it's usually not 2 and -2. It's usually 1 and -1. So I'm going to start by saying, hey, sine of x is between -1 and 1. Same is true for cosine. So typically when I see a limit to infinity and a sine or a cosine, I start thinking, oh, I'm probably going to have to use the squeeze theorem. So then, just like the previous one, I need to make the middle part look like the thing I'm actually trying to take the limit of. In this case, that's going to mean dividing everything by x. Like that. -1 over x is less than or equal to sine x over x is less than or equal to 1 over x. Okay. And then, just like before, I'm going to take the limits of these parts. So the limit as x goes to infinity of -1 over x, well, that's 0, because you've got -1 over a denominator that's getting larger and larger. And similarly, the limit as x goes to infinity of +1 over x is 0 for the same reasons. So the limit of this is 0, the limit of this is 0, and then we can say, by the squeeze theorem, the limit as x goes to infinity of sine of x must be equal to 0. Karen, that depends on the equation. I'm not sure. If you have an example, I'm happy to kind of address it, but it really kind of depends. In this example, that would not change anything, Evelyn. If x was going to -infinity, we would still get the same results, because whether x is going to infinity or -infinity, sine is still between -1 and 1. We still have -1 over x is less than or equal to, there is one small thing it would change, but it's not a big thing. Small thing it would change is this. So if x was going to -infinity, this would still be true. But then when you divided everything by x, technically you're dividing by a negative number, because x is going to -infinity. And when you divide by a negative, you have to change the order of the inequality. But then you would still say the limit of this is 0, the limit of that is 0, and so this thing is stuck between them and is still 0. So no, it wouldn't really change anything. But yeah, that's an important thing to remember. When you divide or multiply by a negative, you do have to change the direction of the inequality. A similar example, but not quite the same, it would be something like this. The limit as x approaches 0 of x squared times cosine of 1 over x. Here, I still see the same sort of thing happening because even though x is going to 0, 1 over x is getting infinitely large. And cosine of something that's infinitely large is, I don't know, right? Cosine is just, it's doing the cosine thing. It's going up and down and up and down and up and down and up and down. So once again, we're going to say, well, I don't know what cosine is, but I know that cosine of anything, right? It doesn't matter what's in there. Cosine of anything is always between -1 and 1. It's always true. Cosine for cosine and sine. Other trig functions is not true. But for cosine and sine, no matter what you're taking cosine or sine of, you're always between -1 and 1. And then we can do the same thing we did before. I'm trying to get the limit of x squared times cosine of 1 over x. So I'm going to multiply this whole expression by x squared. So you get negative x squared is less than or equal to x squared times cosine of 1 over x is less than or equal to x squared. And then the limit as x goes to 0 of negative x squared is 0, right? We just plug it in, we get 0. And similarly, the limit as x goes to 0 of positive x squared is also 0. So then we can see, oh yeah, x squared times cosine of 1 over x is squeezed between 0 and 0. So we can say, I would write it up here, by the squeeze theorem, the limit as x goes to 0 of x squared times cosine of 1 over x is equal to 0. And in fact, I think this one is worth showing you graphically as well. So maybe I still have this one. I can show you it real quick. Let's zoom out. Okay. Let me share this again. Sure. So we can graph these things. So first I'm just going to graph cosine of 1 over x, just because I want to show you what's happening. So, okay, that's not super good job, Dave. So if we zoom in, right, we can see that, oh, wow, yeah, it's just, as you get closer and closer to 0, it is just bouncing back and forth between 1 and -1, 1 and -1, 1 and -1 forever and ever and ever and ever, an infinite number of times. So as x gets closer to 0, this function does oscillate between 1 and -1 an infinite number of times. So the limit doesn't exist, right? If I said what's the limit as x goes to 0 of just cosine of 1 over x, the limit would not exist because it's infinitely oscillating back and forth. It's not getting close to one particular value. However, if we look at these functions, x squared and negative x squared, you can see that, oh, if I was stuck in between them, I would have to be getting closer and closer to 0. And so now if we look at this and multiply it by x squared, turn it on, you can see that, oh, look, it does in fact get stuck, right? It's stuck between those two functions. And so as we get closer and closer to 0, it just gets smaller and smaller and smaller and smaller and smaller. So that's the whole idea of the squeeze theorem, is these outer functions are getting close to some value. And if you're between those two outer functions, you have to get smushed to those two, to that value as well. There's no other choice. Okay. Well, so this is an example of that. This is definitely using the squeeze theorem for trig functions, right? Sine of x is a trig function. So I'm not sure if you mean like a trig function by itself, Karen, or if there's something else you're referring to. So you shouldn't ever have to use the squeeze theorem for a trig function on its own, right? So if I mean, or at least, so if I'm just thinking of like, you know, just a trig function with nothing else, right? It's typically just I'm evaluating this thing. So if someone said, like, what's the limit as x approaches, pi over 2 of sine of x, I'm just going to plug in pi over 2. You get sine of pi over 2, which is 1. Right, there's no squeeze theorem involved here. There's this chair. This chair is too heavy. Ugh, I think I might need to buy a lighter chair. Okay. So I think I've addressed that question, but I'm not positive. Yeah, okay. Okay. Let me see one thing. So okay. I think there's one thing I want to make sure I look at. Yeah, okay. So let's look at problems. I'm going to look at stuff similar to problems 9 and 10 in your homework. Okay, yeah. So we actually, so I will say the problems we just did, like this problem here and that problem there to some degree, this problem here is very similar to problem 9 parts, the second and third part. So you could totally do the second and third part of problem 9 using the squeeze theorem. So I'm not going to do it, but I'll point out that if you had to do, right, the one I see is the limit as x goes to infinity of sine of negative pi x over 2 all over 3x. The way you would do this is by using the squeeze theorem, right? You would say, hey, that's between 1 and negative 1. So then the whole thing is between negative 1 over 3x and 1 over 3x, and the limit of each of those is 0. Now, the first part of that is different, though, and that's actually where I wanted to go next. So I really want to look at the limit as x goes to 0 of something like this. Sine of negative pi x over 2 over 3x. And so, in fact, someone asked the question last class, which I said I would get to this class, which was something like, but maybe not exactly, the limit is x goes to 0 of sine of 6x over 4x. And the problem with these limits is if you plug in 0, you get 0 over 0, which is an indeterminate form, or undefined, but more specifically, it's indeterminate. So what do we do? Well, the question here is how much do you want to know? So let me give you the short version, and then if you guys want, I can give you the longer version. Here's the short version. The limit as x goes to 0 of sine of x over x is equal to 1. You can graph it. I will graph it. Now that I've said you can graph it. In fact, I might be able to give you a semi-decent explanation, not using all the stuff that normally one would have to do. So let's close those. Come on. What happened? My graph went away. Oh, it's because I'm zoomed in too far. No, sorry. There we go. Let me share my screen so you guys can see what I'm talking about. Okay, so here is the graph of sine of x over x. And you can see, all right, yeah, it looks like that as we get closer and closer to 0, yes, we get closer and closer to 1. But I will point out that at 0, right, come on, can I get there? Yes, at 0, it's actually undefined, which again makes sense. Sine of 0 over 0 is 0 over 0, which is undefined. I really, really, really want to stress, and I'm going to stop sharing here, right? 0 over 0 isn't equal to 1 in this case because 0 divided by 0 is equal to 1, right? There are lots of other 0 over 0 types of limits that are not 1. This one's going to end up being 6/4. This one's going to end up being negative pi over 6. So right, there's lots of 0 over 0 isn't equal to 1 because you're saying 0 goes into 0 one time. 0 over 0 ends up being 1 in this case because of the type of limit we have, right? But 0 divided by 0, that could be anything. I think I said this last class, I'm going to say it again. 0 divided by 0 could be 5, because 0 goes into 0 5 times. Or it could be 17, or it could be a billion, right? It could be anything. That's why it's called an indeterminate form. So why does this particular limit happen to be 1? Well, here's the real idea. The idea is that you actually use the squeeze theorem. And if you want, if you're interested, I can show you in office hours, but it is a little bit of a proof. But here's what it basically breaks down to. You can show that sine of x is between cosine of x and secant of x, or 1 over cosine of x. At least for values of x that are close to 0. So if we zoom into 0, hey, look, oh yeah, the green function, sine x over x, is definitely bigger than cosine and is definitely smaller than secant. And so since both of those are getting closer and closer to 1, right, cosine of 0 is 1, secant of 0, which is 1 over cosine of 0, is also 1. Since both of those are getting closer and closer to 1, and sine of x over x is between them, then the limit as x goes to 0 of sine x over x is also 1. Okay, so we're going to exploit that fact a lot. So really, the way I actually kind of think of this even more generally is, it doesn't actually have to be exactly x, right? You could have the limit as some stuff goes to 0 of sine of some stuff over the exact same stuff. And that limit will be 1. Okay. So our job is to make it look like we have sine of a thing over the same thing, and the thing has to be getting closer and closer to 0. So let's look at this example. The limit as x goes to 0 of sine of 5x over x. Well, one of the things is true. The stuff in here and the stuff down there are both going to 0. But the other thing I need to be true is that they're both the same. So what do? I adjust. I multiply by 5 down here and 5 up here. Now I really want to be clear. We're not saying that this is equal to 1. We're saying that the limit of this is equal to 1. Right? This function takes on all sorts of different values with different values of x. But as x is close to 0, this part ends up being 1. So I can say that, oh, when I take the limit, I'm going to get 5 times 1. Notice I'm not writing the limit anymore because I took the limit. I got 5 times 1. Okay. This isn't actually exactly how I usually do it, but it is when I just have I'm missing the coefficient in the denominator. But let me show you a slightly different question. The limit as x goes to 0 of sine of 6x over 4x. Here's what I usually do. I usually break up this fraction into pieces I want, or I mean into separate pieces. So I'm going to write this as the limit as x goes to 0 of sine of 6x over blank times blank over 4x. Right, it's still the same. I haven't changed anything yet, but I've left myself some room to work with. Now let me ask you guys, if I'm trying to get sine of stuff over the same stuff, what do I wish was down here?
6x.
Exactly. But if I put a 6x in the denominator, I have to balance that out with a 6x in the numerator. And then look what happens. The limit as x goes to 0 of sine of 6x over 6x is 1 because the stuff is going to 0 and the stuff is the same. And this part here, the x's cancel and you get 6/4, which reduces to 3/2. Done. So the name of the game usually is to make it look like you have sine of a thing that is going to 0 over the same exact thing. And the limit of that part will be 1, and the rest of it we'll figure out. So to go back to the example I wrote before, which I don't exactly remember, so I'm just going to make something up slightly different. So to do the limit as x goes to 0 of sine of, I don't know, pi x over 3 over, I don't know, 4x. I'm going to do the same thing I did right there. I'm going to rewrite this as, I don't know why I'm using the color here. I'm going to write this as the limit as x goes to 0 of sine of pi x over 3 times something over 4x. And beneath the sign of a thing that's going to 0, I'm going to write the same thing. But if I write it down there, I also have to write it up here, so that I'm really just multiplying by 1. And then we end up with, so this part's going to just be 1. This part, the x's cancel, and you get pi over 3 over 4. And let me ask you guys, is that going to be 4 pi over 3 or pi over 12? Is this pi over 3 times 4 or pi over 3 divided by 4?
Divided.
Clearly divided, right? So it should end up being pi over 3 dividing by 4 is like multiplying by 1/4. So I get pi over 12. And that's our answer. That's what this limit is. So when you've got limits with sine of something over something, and both parts are going to 0, not infinity, right? Infinity, it's a totally different story. You use the squeeze theorem. But both parts are going to 0. You have to do this thing where you get sine of a thing divided by the same exact thing, because the limit of that part, I really should have circled the limit. The limit of this part is 1, and then this is just algebra. Okay, questions about this? And this method, this totally applies to the first part of problem 10 as well, except we have to do more work for that. So let's look at one similar but not exactly the same as what's going on in problem 10. So limit as x goes to 0 of 1 minus cosine of 4x over 7x. All right. So this limit, the way you have to deal with this limit, at least the way I think you should deal with this limit, is by multiplying by the conjugate. One plus cosine of 4x over 1 plus cosine of 4x. Okay. So now, what do you get when you multiply out the top? Well, on the bottom, I get 7x times 1 plus cosine of 4x. And on the top, I get 1. I get plus cosine of 4x minus cosine of 4x, which cancels out. And then I get a minus cosine of 4x times a cosine of 4x, which is minus cosine squared of 4x. And that's a trig identity. 1 minus cosine squared of an angle is equal to sine squared of that angle. So I can rewrite this as the limit as x goes to 0 of sine squared of 4x over 7x times 1 plus cosine of 4x. In case anyone's not clear on that, I'm just using the identity that sine squared of theta plus cosine squared of theta is equal to 1. And I'm solving for sine squared and saying sine squared equals 1 minus cosine squared. All right, and now I'm going to do the same thing I did before. I'm going to break this up into pieces I want. I'm going to write this. Well, I'm going to break it up into just pieces and then make them what I want. I'm going to write this as the limit as x goes to 0. Sine squared of 4x is sine of 4x times sine of 4x. And I've also got a 7x and a 1 plus cosine x. Cosine 4x, sorry. Okay. You guys help me out. What do I wish I had down there? That's right. People are writing things in the chat way down there. Almost 4, a little bit more. Yeah, 4x. So if I put one down there, I need one up there. Now I will point out you could actually stop here and you could say this is going to be 1. The x's here totally cancel. This is going to be 4 over 7 times 1 plus cosine of 0, which is 1. And then this is going to be 0 because sine of 0 is just 0. Or you could also put in another 4x here and another 4x here. Either way is fine, but look what happens. The limit of this is 1. The limit of this is 1. And the limit of this is 4 times 4 times 0 over 7 times 1 plus 1. And once you say times 0, the story is over. You have multiplied by 0, you get 0. So this limit's 0. And typically, any kind of 1 minus cosine x over x limit as x goes to 0 is 0. So this limit does kind of become important. Maybe not so much in this class, but more specifically, the limit as x goes to 0 of 1 minus cosine x over x is equal to 0. Now, it's not true if it's to infinity. Right? If you did the limit to infinity of this expression, you would have to use the squeeze theorem. And so now here's the thing you should get kind of used to seeing with this. Limit as x goes to infinity of 1 minus cosine of 4x over x. Let's actually go to negative infinity just for fun. Doesn't really matter. Oh, sorry, 7x. Here's what I know is happening. I know the denominator is getting negatively infinitely large. I know the numerator is kind of just bouncing around between two numbers, right? 1 and negative 1, or maybe 2 and 0, or something like that. I don't know. I know it's not getting bigger. I know it's staying kind of small. So the top is small, the bottom is large. Small thing divided by large thing is a small thing. So this should end up being 0. Here's how I would actually do it. I would start with this. Cosine of 4x is between 1 and negative 1. Negative of all that. So here's the thing. If you take the negative of that, yeah, you could flip everything, right? And say, okay, this is now bigger than or equal to negative 1 and less than or equal to 1. It's still the same inequality. It's just written backwards. And then I'm going to add 1 to everything. So that 1 minus cosine of 4x is less than or equal to 2, is bigger than or equal to 0. Divide by 7x, divide by 7x, divide by 7x. And then 0 divided by 7x is just 0. And the limit of 0 is 0. 2 over 7x, if you take the limit as x goes to negative infinity, is also 0. So the limit of that is 0. The limit of that is 0. So the limit of this has to be 0. And the squeeze theorem doesn't always give you 0, but it gives you 0 a lot of the time. So when you see something where you think you're going to use squeeze theorem, it's not a bad bet that you might get 0. All right, let me see. Sorry, 1 second. I'm just looking back at the. All right. Okay, yeah. So I see some things about derivatives, tangents, intermediate value theorem. Okay. Have we talked about the intermediate value theorem in class here?
I
I've definitely talked about it in the other class I'm teaching. I just couldn't remember if I talked about it here or not. So let me see. Let me actually look at one thing. Nope, actually. Okay, yeah, that's fine. Okay. Okay. All right. I just trying. I don't see any questions on your homework that you really have to do. That doesn't mean we shouldn't cover it. This was trying to look for inspiration. So the whole deal with the intermediate value theorem is that you can use the intermediate value theorem to either say a function has an x-intercept, or to say that some equation has a solution. Those are, and they're really kind of very related to each other, and we'll talk about them both. So one kind of typical question is something like, okay, use the intermediate value theorem. So use, which we often abbreviate as the IVT. Use the intermediate value theorem to show that the function f of x equal to x cubed minus 5x plus 1. Make sure I didn't pick anything that was too stupidly easy. No. Has an x-intercept. Meaning has a place where the function is equal to 0. Okay. So the gist of the intermediate value theorem, there's always like two things you have to do. The first thing you have to do, oh, and I should say, sometimes they give you an interval. Right? Sometimes they say, show there's an x-intercept somewhere. Sometimes they say, show there's an x-intercept between x equals -10 and x equals +10, or something like that. The way where they give you the interval is usually easier. Let's do this one where we don't have the interval first. So first and foremost, you have to say something. Observe, note, we know. Something about the function being continuous. We know that this function f of x equal to x cubed minus 5x plus 1 is continuous everywhere. Not every function is continuous everywhere. It doesn't have to be, but you do have, for the theorem to be applicable, the function does have to be continuous on the interval you're looking at. Because essentially the idea here is that you have to have a function that doesn't have any weird jumps or breaks. And here's why. Because the second part, we're going to say the following. So if you're trying to show that this is equal to 0, which is what you're trying to show, if you're trying to show as an x-intercept, you want to find a place where it is positive and where it is negative. So I'm just going to pick some values, and I almost always try x equals 0. So plug in x equals 0, and f of 0 is going to be 0 minus 0 plus 1, which is positive. And then pick another number, and we're going to try and pick something that we think will make it negative. I'm going to try 2. I probably would actually try 1, but I'm going to try 2. We plug in 2, and get f of 2 is 2 cubed minus 5 times 2 plus 1, which is 8 minus 10 plus 1, which is -2 plus 1, which is -1. Great. So here's what that means. It means, in fact, I'll draw a picture in a second. Over here, the function, let me draw the picture. We'll come back to this in a second. So here's what that means for us. It means we know that f of 0 is 1. And f of 2 is -1. And the function's continuous, meaning I can't just be like, jump, right? That's not allowed. I can't do that if the function's continuous. So there has to be a place between 0 and 2 where the function crosses the x-axis. There's no way to get from a positive y value to a negative y value if the function is continuous without actually crossing the x-axis. So what we can say then is by the intermediate value theorem, there must be a number. We often call it C for some reason. And that C, right there, C right there. I don't know what it is. We almost never know what it is. But C, C is between what two numbers?
0 and 1.
Well, the way I've drawn it, yes, but we didn't actually use 1. So we used 0 and 2. But it is also correct, right? If you went back and plugged in f of 1, you would get 1 minus 5 plus 1, which is also negative. So that would also work. But you have to use whatever boundaries you have particularly picked. So since we did f of 0 is positive 1 and f of 2 is negative 1, we know that our answer lives somewhere between 0 and 2. Such that f of x equal to x cubed minus 5x plus 1 has an x-intercept. That's the whole idea. You say, oh, the function's continuous. The function's positive somewhere. The function's negative somewhere. So since it's continuous and it goes from positive to negative, it has to cross through 0. That's it. That's the whole idea of the intermediate value theorem. Let's do another example. So show that, sure, let's not make it dumb. That 3 to the x equal to x squared has a solution on the interval from so this time I gave you the interval. So that this equation, 3 to the x equals x squared, has a solution on negative 1 to 0. Here's what I don't want to do. I don't want to just say, I always don't like it when it's an equation like this. Because I'm like, well, if I plug in 0, this is 1 and this is 0. If I plug in negative 1, this is 1/3 and this is positive 1. So at one spot, this one's bigger. At the other spot, this one's smaller. But that feels complicated. Here's what you should always do if you're trying to show that some equation has a solution. Reimagine it. Instead, we're going to show that 3 to the x minus x squared equals 0 has a solution on the interval from negative 1 to 0. Because then I can just do the thing I did last time, where I show that it's continuous, and I show that it's positive somewhere and it's negative somewhere. That is always the way you want to do it. It is always easier to say, I'm going to try and show something has an equal to 0 has a solution by showing it's positive somewhere and negative somewhere. So don't do this, do this. And then we're also going to be smart, and we're going to say, I'm going to call this f of x. So f of x is 3 to the x minus x squared. Okay, so step 1, first and foremost, you shouldn't have to actually show it's continuous. You just have to say something about it being continuous. So f of x is continuous. Again, this function is continuous everywhere. 3 to the x is an exponential function. It's continuous everywhere. X squared is a polynomial function, continuous everywhere. And the sum or a difference of continuous functions is continuous. Okay. So then, here we were given endpoints. So we can just check. F of negative 1 is equal to 3 to the negative 1 minus -1 squared. 3 to the -1 is 1/3 minus -1 squared is 1. And 1/3 minus 1, I don't even really care what the value is. I just care that it's negative in this case. But you could say it's -2/3, which is negative. And then f of 0 is 3 to the 0 minus 0 squared. 3 to the 0 is 1 minus 0 is 1, which is positive. And then we write the words at the end. By the intermediate value theorem, there is a number C. Where does C live? Between, okay, let me ask you guys, does C live between -2/3 and 1 or between -1 and 0?
-1 and 0.
Yeah, C is the X value, right? C lives between other X values. So C lives between -1 and 0. Not everybody makes you say this, but I think it's important to say this, right? You're talking about finding, or at least saying there's a solution to this. It's good to give an idea of where the solution is. The solution is somewhere between -1 and 0. So there's some value of X, maybe it's like -1/2. It's not, but it's like around there, where 3 to some power equals X, that same number squared. Such that, and I would just write at the end, such that f of C is equal to 0. Right, that's kind of the easiest ending. All right, I think we should do one more. Yeah. Okay. Show that natural log of x equal to 1 over x has a solution. Step 1. We want to show instead that f of x equal to, I don't really care which way you write it, you can write it as natural log of x minus 1 over x, or 1 over x minus natural log of x. We want to show that this equal to 0 has a solution. Okay. Here, we have to be a little bit more careful about the next part. Observe, note, say something about the fact that f of x is continuous, but not everywhere. Right? Definitely not continuous at 0. Right? It's not defined at 0. It's definitely not continuous where it's negative because it's also not defined where it's negative. Right? This function is only defined where x is positive, right? Natural log of x is only defined where x is positive. So this is definitely continuous on the interval from 0 to infinity. So we're limited, right? We can only use values between 0 and, I mean, it's still a lot of values to use, right? This is also where having a good idea of what the graph looks like is going to help you pick numbers. So I know that the natural log of x looks like this, has an x-intercept at 1, 0. I know that 1 over x looks like this, and I know it has the point 1, 1. And it definitely looks like they have to cross somewhere. But it looks like they're definitely crossing after 1. So what I would do is I would say, well, I'm going to plug in x equal to 1. And f of 1 is 1 over 1 minus the natural log of 1. 1 over 1 is 1. Natural log of 1 is 0. So it's 1. And then I'm going to try and plug something else in that's going to make it negative. Now here's the thing. Something negative. So the problem is, like, if I try x equals 3, I get f of 3 is 1/3 minus natural log of 3. I don't really know what the natural log of 3 is without a calculator. And yeah, you can totally use a calculator and see that this is negative, but I would rather pick a value that I'm better at evaluating. So instead of 3, I'm going to pick E. Because we know that the natural log of E is equal to 1. So this is 1 over E minus 1. And although I don't know what 1 over E is, I definitely know it's smaller than 1. Because E is about 2.7, and 1 divided by 2.7 is definitely way smaller than 1. So this is definitely smaller than 1 minus 1, which is 0. So here it's bigger than 0, here it's less than 0. So we've done it, right? Then we just have to say the words, right? By the intermediate value theorem. So I would at the end say by the intermediate value theorem, there is a number. I'm calling it C. It's between 1 and E such that f of C equals 0. So as you might have started to notice, these intermediate value theorem problems are all kind of the same, right? You're trying to show this a solution. First, you show first you try and say I'm going to set it equal to 0. Then you say it's continuous. Then you find a place where it's positive, a place where it's negative, and then you say, great, I did it. Here's what you get. So that's the intermediate value theorem. Do something here. Take some screenshots of your names real quick here, just so I can make sure I can get everybody. There are a lot of you. Okay, good. Sorry, let me go back to the. So if the function isn't continuous everywhere, Julia, then, well, I should say, the function has to be continuous on the interval you're using. So as long as it's continuous on the interval you're using, it works. If it's not continuous on the interval, then you're right, it doesn't work. For example, sometimes people ask questions like, why doesn't this equation have a solution? Like, for example, let me try and think of something that's, so like, why doesn't, ish, 1 over x minus 2 equal to, sorry, let me make this bigger. Let's say 3 over x minus 2. Sorry, come on, brain. Sorry, 1 second. I've almost got the example in my head. Yeah. Why doesn't this have a solution on the interval from, say, 3 to, sorry, not 3, from 1 to 3? And so if you weren't being careful, you might be, well, like, okay, so I'm looking at f of x equals 3 over x minus 2 minus 1. I can see that f of 1 is equal to 3 over 1 minus 2 minus 1, which is 3 over negative 1 minus 1, which is negative 3 minus 1, which is negative 4. And f of 3 is, did I pick a dumb number? No, 3 over 3 minus 2, which is 3 over 1, which is 3. And so if we're not paying attention, we're like, well, it goes from negative 4 to 3. It should hit every value in between. We should be able to get 1. Why don't we get 1? Well, because it's not continuous. Right? If you graph this thing, we know that f of 1 is negative 4. Sorry, yeah. So 1, negative 4. And f of 3 is 1. And so you're like, well, wait, if it's continuous, it should be like that, right? But it's not continuous, right? We know we have a vertical asymptote at 2, What's actually happening is it's doing this. So yeah, of course you're not getting any values between those, right? Because it's not continuous. So